This is lecture 10A for Calculus 2 on parametric equations. This is the introduction to parametric equations. There's two ways that parametric equations arise. Some occur naturally in applications such as projectiles, and the others are for mathematical convenience. And sometimes it's very convenient to describe a curve by parameter. What parametric equations are is a set of equations. In this class we only work in two dimensions, so this is a set of equations, one for x and one for y. Both x and y depend on a third variable, often it's t, time, and that variable is called a parameter. That's why they're called parametric equations. Each equation could be thought of as a separate equation, but they're also combined. So here's an example of parametric equation. You have x and y. Here's your two variables right here. Both of them depend on another parameter called t, and they are linked through this parameter called t. Let's say x varies as a cosine of t and y varies as a sine of t. Right, t is called the parameter. These combined are called parametric equations. You might have seen these in trig. Now, you could plot x and t separately, and then they would be on x and t axes. So, well, x or y. So here's your x plotted against time, right here. X is plotted against time. You see it's a cosine curve with an amplitude of 10. Here's y plotted as a function of time. It's a sine curve with an amplitude of 10. Now, instead of plotting them separately, we could plot them together. At every instance of time, t, say t equals 0, 1, 2, 3, 4, 5, x and y will have corresponding values corresponding to that particular time. You can plot those values, x versus y, on the x and y plane. Here we have x, these were the equations we saw before. X varies as a cosine of t, y varies as a sine of t. But at each point, for example here, when t is 0, then x, in this case, had the value 10, y had the value 0. That became this point right here. As time moves, let me get the pen, as time moves, you trace out the curve in this direction shown. Okay, example, at this point, x and y, this is a point in time in which x and y have these particular values. This is another point in time in which x and y have these particular values. So these are corresponding points in the xy plane. Each one corresponds to some kind of t. Right? Now, the one thing that you lose when you plot it this way is that you lose how fast the curve is being plotted out. All you do is see x versus y. For example, this curve could be traced many times over and over and over, which it is as t increases. Every time you go through these cycles of x, of sine and cosine, you're retracing this curve. And if I hadn't put the arrow on here, it wouldn't be clear the direction that the curve is being traversed. But you've now seen two views of this particular, these particular parametric equations. Now we'll look at an example of a naturally occurring one from physics. We're going to consider a projectile that's fired at some angle theta with respect to the ground. Now it has two components. Sometimes it's a little hard to understand. It has an x component, okay, and this is its velocity in the x direction, and it has, well, let's make that vertical component, and that vertical component is a velocity in the y direction. So if I take that velocity of the projectile at the instant that it's, and I can divide that into two components. The x, let me make that look a little bit more like an x. The x velocity in the x component of the velocity in the x direction, and a horizontal or vertical component, which I'm going to call vy. And here they are right here. This is just the usual vector analysis where you divide it up into x and y components, orthogonal components. Now, the motion in each direction is subject to different forces. In the x direction, we're going to neglect air resistance, okay? So in this x direction, the equation of motion is your starting point, x naught, plus the velocity times time. There's nothing, if we've neglected air resistance, there's nothing impeding the motion in the horizontal direction. You might think the gravity is acting on it, but it's acting perpendicular. The effect of gravity is considered in the y equation. So here is the y component of the motion. Y of t is y0, that's the launch height, plus the velocity in the y direction times time minus 16t squared, well, acceleration due to gravity divided by 2. Here we're using British units. And so that's this term right, whoops, need a pen. This is your gravity term, and it only affects the y component. So now we have two separate equations. They are linked by the parameter t because as the projectile traces out its path, the x component and the y component of its motion are linked. Okay. We can plot these separately, and then we can plot them together. I'll do that on the next slide. So we needed some numbers. So here's a crossbow. It has an initial velocity. The magnitude of the initial velocity is 242 feet per second, and it's was shot at a 30-degree angle from the ground, from the horizontal direction. So remember, it had two components, a horizontal and a vertical component. So here's its horizontal component, and this is just linear, which is what that equation was, right? It was x naught plus velocity in the x direction times t. That's just a linear equation, and its slope is the x component of velocity. Here's its height. If you remember, that was a parabolic equation. It had the extra term. That extra term was the acceleration due to gravity that's pulling the projectile back down. So this is how it behaves in time vertically. Let me try to draw that for you. So we have two motions here. We've got a motion that's going horizontal. I'm trying to draw with the mouse. Sorry about that. And vertically, it's going to write right over itself because it's totally vertical. But if I spread that on time, it is a parabola. Now, I can plot y versus x, and now I get the spatial path of the parabola, of the projectile, which is also a parabola. So this is combining the two parametric equations, y versus x. And the others up here, it was y versus x versus time, and y versus time. And this just happens to turn into a parabola. They don't always turn into exactly the same thing. Right? Again, we don't know how fast it's going in its motion, and we could probably draw an arrow on here to show you the direction that it's going, but that's not apparent once you plot x versus y. In the example before, for the projectile, y was a function of x. It would have passed the vertical line test. This is not necessarily true for projectiles. It's not necessarily true for parametric equations in general. And what I'm showing here is a path of a model airplane, and you can see that it definitely is not. It's not a function. It's also kind of interesting because it appears to have plotted into the ground here, since this is here is ground level at x equals 0. Maybe it went into some water. I knew someone who ran their model airplane into a swimming pool full of people. They got scared and all got out before that happened, thinking it was a real plane. At any rate, what you're having here is the path of this projectile with respect to time, or with respect to distance. This is y, this is x. But each component could have been plotted separately as a function of time.